So many of you have asked for details about how the cache coherence protocols are implemented on the bus during the lectures. So I decided to add this extra video here explaining exactly what goes on when you interact between back-to-back race conditions in cache coherence implementations. I'm going to show you an example once more from Enterprise Server 6000, which is also similar to how the Intel P6 system was implemented. We're going to talk about the split transaction buses. So split transaction buses, it's a bus where you can send out the request, and then within some finite time, some kind of data response will follow. So we're going to talk about address transactions or request transactions that are coupled to some kind of data transactions. So the data transactions and the address transactions logically are sent along different wires implementing that bus. Before you send a transaction on the data signals or on the address signals, you have to arbitrate for that bus to make sure that we don't collide. We don't want lots of caches to send transactions at the same time on these wires. So we have the arbitration signals. Could be one or many signals implementing the arbitration algorithm. And over time, this is how it works when you would like to send a transaction on the bus. If you like to send an address transaction, you arbitrate for the bus. And here we arbitrate for our first address transaction. If the arbitrator when the arbitrator tells us it's our turn to send the transaction, we'll send the address transaction on the bus together with the encoded request, read to share, read to write, and so on, as well as some unique identifier, ID1 in this example. We arbitrate for the bus again to send the second transaction, and if we arbitrate for the bus to send the third transaction and the bus is busy, we have to wait until it's our turn to send the transaction. So eventually, back to back, we'll send the third address transaction with the request encoding as well as some unique identifier. It is a split transaction bus, and that implies that the replies to these requests may actually come out of order. So the reply to the second request, the data packet answering the first request, may actually be returned before we get the data packet returning the data associated with the first request. And just to be able to keep these apart, we make sure that these data packets have the same unique identifier as their corresponding address request. Of course, before you send a data transaction, you also have to arbitrate for the data bus using some kind of putting some kind of signals on the data arbitration lines and so on. Furthermore, in order for this kind of transaction to work, we will have to introduce some buffering between the Snoop state machines as well as the bus. So if the Snoop state machine sees there's a need for us to send something on the bus, we can't expect to immediately get the bus. Instead, we just queue up these responses or replies that we would like to send, put them in a queue, and eventually we will be able to get a hold of the bus and send those transactions. So this is the buffering is required so we can avoid deadlocks, but the buffering will also create some kind of race conditions later on that we will have to solve. So the timing of this kind of transaction is quite intricate, and it's very well engineered together with a kind of SRAM technology, how fast we can do lookup in caches and so on. So in this example here of how this can be implemented, we have the big bulk of all the wires of the bus. It would be the address wires as well as the data wires. But we also have, so on the address wires we send the address request and ID, but we also have some other wires here. Some wires called the Snoop result wire, where you can send share and own response. We have the arbitration wires, where you either every other cycle can arbitrate for the address bus or the data bus. And up at the top here, you see the cycle count. So this is cycle by cycle. It's a synchronous bus. So first cycle, second cycle, and so on. And that's sort of the progress of time going that way. In this diagram, we also show some number of latencies. So there's a fixed latency between the arbitration. You arbitrate for the bus, and in the same cycle, in this implementation, you may actually put the address the request encoded on the bus. The very next cycle, fixed latency, the next cycle, you will put the unique identifier of that transaction. And within some finite time, you will, after a fixed number of cycles, this is the time when the caches can choose to raise their arm, voting shared or voting owned the following transaction. The dashed line here shows a flexible latency. This is actually the earliest it can happen. So if board number 1 sends the read request and board number 2 wants to reply with the data corresponding to that request, this is the earliest point in time it may arbitrate for the data bus. After 2 cycles, it's going to send the unique identifier corresponding to the data it would like to send. In this situation, it's replying to the first request, so it's going to have the same unique identifier down in the address packet as we did in the data packet as we did in the address packet. Later on, it's going to be some data status. In this example here, it says OK, and at the tail end of these 2 coupled transactions are the 2 data packets that are sent. It takes 2 cycles to send an entire cache line using this design. I already said that there is a buffering going on between the Snoop protocols and this bus. So at the top here we have the bus with all the signals of the bus, and you can drive the bus or you can listen to the bus. And at the top we have the coherence protocol, the snooping cache coherence protocol, and that state machine we discussed before. It's a dual tag design, so the Snoop cache coherence protocol looks into the Snoop tags. Here we have an input queue that we can buffer some requests. At close to the cache is the CPU Snoop coherence protocol, and attached to the cache is the state, and we know it really is integrated in the cache, but I did break it out here so we much easier can discuss what's going on. So this is the cache where we have 2 different cache lines, cache line A and B, both in state shared, which means that the Snoop tags are also for A and B in state shared up here. So the coherence protocol will examine what kind of transaction the CPU wants to do. So the CPU wants to perform a memory instruction, store to the cache line A, and we have the cache line A in state shared. So according to the MOSI protocols that we've been discussed earlier, what bus transaction will be sent up here on the Snoopy bus, on these wires up here, caused by the fact that CPU down here wants to store to a cache line in state shared. So the transaction that will be sent is an invalidation transaction. So we're going to queue up the invalidation transaction in this output queue, OQ, and it's going to stand here, and it will start to try to arbitrate for the bus, and it's going to be stuck here in this queue until we manage to arbitrate for the bus and we can send out this transaction. While it's standing here, the CPU can potentially queue up other transactions, other requests behind it. So while it's standing there waiting to be sent on the bus, another transaction will be snooped on the bus. So we'll say a foreign read-to-write request for the cache line B. So that will force the Snoop tags to go from state shared to state invalid, and we're going to queue up the foreign read-to-write transaction in the input queue on its way down to make modifications to the CPU tags. It's going to be stored here until the coherence protocol, the lower coherence protocol, feels like it's time has the time to pay attention to this request. When it does so, it will of course go down and invalidate the cache line B in the CPU tags, so it will be in state invalid in this cache. So that went all well, but let's look at a situation where a race condition can be created due to the buffering and the dual tags. So once more, the CPU wants to store to cache line A. It sends out an invalidation transaction up here because it already has the data in state shared, and all it wants to do is to invalidate everybody else. Meanwhile, there is a request, a foreign request, somebody else who sends a request on this bus, and this other cache wants to perform a read to write of exactly the same cache line. That means that the Snoop tags will go from state shared to state invalid, and then we'll queue up the foreign read to write request to cache line A in the input queue until the lower coherence protocol has time to pay attention to it. When it does so, we'll change the state of cache line A to invalid. This is where the race condition, the first race condition we're going to discuss, has occurred. Because we wanted to send out an invalidation request on the bus, because we felt that we already had a copy of the cache line and all we wanted to do was to destroy all the other copies in the world. However, while that request was stored in the output queue, the foreign read-to-write request invalidated our cache line in the Snoop tags, as well as invalidated in our lower cache. So we no longer have the cache. What should we do now? Well, we actually have to change the cache coherence protocol to adopt to these kind of changes. So the state transition diagrams that we discussed in class will not hold for this kind of implementation where we have buffers and dual tags. So to implement MOSI on the split transaction with dual tags and buffering, we need to handle several corner cases, one of which we just looked at. And in order for us to do that, we will actually put a dual role on some of the transactions. We will actually only have 3 bus transactions instead of the previous 4 bus transactions. And what we'll do is we encode the behavior of invalid and the old behavior of read to write in the same transaction. So even when we want just to invalidate the rest of the world, we will send a read to write transaction. So when we perform a store, we put the read to write transaction in the output queue, even if we already have the data. Now we have to modify the protocol slightly. So what we do is that when we manage to send our own read to write transaction, so my read transaction, when we see my read transaction on the bus, we will assert the shared Snoopy line of that bus if we still have the data. And what this in essence will do is to tell everybody else that whoever is putting a read to write request out there already has the data. But we wait until the point in time where our own transaction is on the bus to tell the world whether we have the data or not. If we see a foreign read to write request where that shared line on the bus is asserted, we will treat that as the good old invalidate bus transaction. So this is a transaction where everybody else understands that all they need to do is to invalidate their cache lines in their cache, and they will not have to provide the data because whoever sent out this request asserted the shared line. Furthermore, when you see a foreign read to write request for a specific cache line, you assert the owned line on the bus if you have the data in state modified or state owned. That tells the rest of the world that or more specifically tells the memory that the memory no longer has to reply to this request because some cache either has this cache line in state modified and owned, and their intention is to reply to this request. Furthermore, if you see a foreign read to share request and you have this cache line in state shared, what you can do is to raise your arm, or if you're in state shared or in state owned or state modified. So in essence, if you have the data and for the cache line for which you see foreign read to share request, you raise your hand by raising this shared signal on the bus, and that signals to everybody else that there is already a shared copy in a cache, and that prevents the requester from going to state exclusive. So you remember this Moesi protocol, it was a choice of going to state exclusive, and that is prevented by inserting the shared line. Also, likewise, as we did for the read to write request, if we see foreign read to share request and we have the data in state modified or owned, we will raise the owned line, which will in essence cancel all data transfer from memory. Finally, if we see our own write back request occurring on the bus, so we manage to arbitrate for the bus and we put our own write back request on the bus, we insert the own signal if we no longer have the data in our cache. So there could be a situation where we start to perform a write back, and before that write back manage to arbitrate for the bus and get on the bus, somebody else invalidates us. That means that we no longer need to do a write back request. Invalidate us, actually that cannot happen. If we queued up a write back request, nobody can invalidate us, but somebody can send a read to write request. That means we no longer should do the write back, and that we signal that by raising the own signal, which in essence will cancel the write back, so the memory will understand, as well as we will ourselves understand that we no longer need to do that write back. So after that long monologue going through all the different fixes for corner cases, let's take a look at exactly the same corner case as we studied before. So we once more would like to perform a store operation to a cache line A, and we have that cache line in state shared. According to these new rules, what transaction should be sent on the bus? What transaction should be sent on the bus to handle that corner case? Well, if you were fast, you already saw that I did put out a read to write request. That's exactly what's the fix. We no longer ever send out an invalidation request. We try to put the read to write request in the output queue, and whenever that read to write request makes it on the bus, then we can vote to tell whether or not we still have that cache line or not. However, similar to the previous case, a foreign read to write request comes in, which invalidates our cache line, first by changing the snoop tags, putting it in the input queue, and then later on by invalidating the CPU tag. So from this point in time, we no longer have neither read or write access. But don't worry, we don't have a problem anymore, because we're going to send the read to write request. And once we see our own read to write request on the bus, right here, the read to write request is on the bus. We can vote to say whether or not we feel that we already have a valid copy. So we sort of snoop our own snoop tags here, and since our snoop tag says invalid, we choose not to raise the shared signal on the bus, which tells the world that we actually will need a piece of data, a copy of this cache line to be sent to us. We snoop our own transaction, which means that at that point in time we change the snoop tags to modified. We queue up our own my read to write request in our input queue. However, this read to write request needs to sit here at the front of this queue, blocking any other requests from being read from this queue until the data associated with that transaction is returned from either from memory or from some other cache, depending on what state they were in. Once that data is returned, that's the point in time where we actually can pop my own read to write request from the input queue and change the state in our CPU tags to state modified. Now we can write that piece of data. Now going back and looking at the timing of different signals on this bus. So we have chosen here to design this snoop protocol such that the time it takes to snoop in a cache, it corresponds to the latency between you put out a request and the address associated with that request, and the point in time where you should raise your shared arm, or the cycle after that raising your own arm. So that is carefully chosen. We've also carefully chosen that the shortest latency you can have between raising your own arm and producing this OK signal here is such that you actually have you have the chance to, if you see that that you already started to arbitrate to reply with a data transaction, but you see somebody else raise their own arm, that means that you no longer should reply with the data. So instead of putting an OK here, you can put a cancel pattern down at this point in time, which means that nobody will ever pay any attention to these pieces of data that you put on the bus. So that's